Hello everyone, and now I would like to continue from the previous lecture. From the previous lecture, what we did is to find out the network in the above pinch and below pinch. Before we doing the combination of these, we have to understand the following configuration, the following specification of this equation first. Of course, we would like to work on how much does it cost for this system. I mean, all the network we have, including the utilities and also heat exchanger we have in here. In this case, the cooling water that using here will have the supply temperature of 30 degrees Celsius and the target not greater than 80 degrees Celsius, with the cost of cooling water of about $0.00015 a kilogram of cooling water, and also the steam that using in for the heating utility. The steam that we are using with a temperature up to 58 degrees Celsius that contain the condensation enthalpy of 116.76 kilojoule per kilogram of steam. And of course, we buy the steam with the cost of $0.006 a kilogram of steam. They also set the overall heat transfer coefficient for heater, cooler, and heat exchanger with 1 and 0.75 respectively. And the way to calculate the heat exchanger based on the area 1/2. Okay, in this case, we need to convert the investment to 1 year. So we will find the price, the cost of operation based on 8,500 hours per year. Alright. Then the first thing to do is just put above pinch and below pinch together under the pinch line. Okay, after that, what we do the next is to calculate or estimate the minimum number of heat exchanger. In this case, the heat exchanger under our roughly estimate is that we have 6 heat exchangers and 2 utilities. Now let's see what would be the minimum number of the heat exchanger that should be provided for this system. The minimum number of the heat exchanger, this is the second one. So we check for the minimum number of heat exchanger, and it is equal to the number of streams using in this supply to this system plus utility streams that we have minus 1. So in this case, we do have 4 streams. We do have 4 streams, 1, 2, 3, 4, and then 1 heater and 1 cooler, 1 cooling system. So we can put in the equation as 4 plus 2 minus 1 equal to 5. So the number that we have is 8. Of course, is higher than what the minimum number of heat exchanger based on the theory is. So 3 heat exchangers should be removed or delooping or deloop. Before doing that, we have to understand how to estimate the cost of the initial system we have in here. So let's see. If I consider the first heat exchanger between the hot stream of 180 degrees Celsius, down to 150 degrees Celsius with 140 up to 160 degrees Celsius with a heat load of 60 kilowatt. So what is the price of heat exchanger should be? So remember that the overall heat transfer coefficient for heat exchanger is equal to 0.75 of this heat transfer. And the equation for the heat exchanger is 3000 multiplied with area 1/2. So let's see. In this case, I already have this spreadsheet that will show you later. Let me explain this first. The first heat exchanger has the heating load of 60 kilowatt, and we have the inlet outlet of hot stream, inlet outlet of cold stream. And according to the overall heat transfer coefficient and capital cost of heat exchanger based on this. So first, what we do is to calculate the delta T log mean. This delta T log mean equal to difference of this part minus difference of this part divided by natural log of this part divided by natural log different temperature of this part. So I think you should familiar on that. And then the area will be equal to Q divided by U and delta T log mean. So the area for the first heat exchanger is equal to 5.5 square meter. And then I put that in this equation. And then what I get is purchase cost or capital cost of the heat exchanger is equal to $7,000 on this unit. Okay. The second heat exchanger would be the same. So second heat exchanger starts from inlet temperature of 150 down to 140 and 126.67 to 140. So let's see what I can get. Under the heat load of 40 kilowatt. So just put it in this, and then the calculation showing that the purchase cost of this unit is about $6,400 on this unit. Now let's see if I can do that on the heat exchanger number 3. Number 3 start from 140 down to 110, and then that will transfer to heat up the temperature from 83.85 to 130 degrees Celsius, I think. 130 degrees Celsius, this should be wrong. So what can I do? I then jump to this and then go to change the temperature of that. See that the temperature should be 130. Okay. Suppose I change that to be 90 degrees Celsius. So the number will change. So let's put it in the same number that we have in the example. So let's see. How can we calculate the delta P log mean? The delta T log mean is equal to blue one minus green one. And minus, the difference temperature of these two. And then divided by natural log of this side as a ratio of this side and that side. Okay. How about the area? The area will be equal to Q divided by U and delta T log mean. Delta T log mean on the purple one here. So what I get is the area, and then plug that in this equation. So 3000 multiplied with this square root of this area. So I get is the purchase cost of this heat exchanger. We do that for the all heat exchanger. We have 6 of them. Then let me go back to the slide. Now this is these 2 slides showing how to calculate as an example of heat exchanger, 2 of them. And now I would like to show how to calculate the utilities. Okay. In the utilities, we set the steam at 258 degrees Celsius to heat up the temperature from 160 to 180 under the heat load of 60 kilowatt. And the price of the steam is equal to this number. Under the evaporation heat or latent heat of 1676 kJ per kilogram. So what we do, rather than the equipment, so we go to find out how much the steam used annually, and then multiply this amount, this steam used annually, with the cost. You will get this number. Okay, let's see. In the spreadsheet, okay, we go to this one. How can I calculate? I use the heat load divided by the evaporation or latent heat, and then change the second to be hour and multiply with the working load of 8,500 hours per year. Okay, so what I get is the number of steam using. Okay, this already shown in this handwriting here. So what you get is the heat load divided by the latent heat and then multiply with the unit conversion and the working hour per year. So what I get is the number of steam using, about million kilogram per year. So I can get the steam cost annually. How about the cooling system? In this cooling system, the way to calculate the water using is based on MCP delta T. So what I get is the number or M dot that would be equal to the heat load spending there, and then the temperature change from 30 up to less than 80 degrees Celsius, or what I using here is 75 degrees Celsius, and then divided by the CP. I multiply with the same amount of this. So we need cooling water around 25 million kilogram per year. Then we can take the cost of the cooling water here by multiply with the price. Okay, and now I can make the conclusion that upon the heat exchanger of 6 we have, so the total area is this, and then the cost is equal to 3000 multiplied with the area, square root of area. The same thing for the heater. So this is the capital cost. So I make the summation of these 3 to be the price of capital cost, or I mean heat exchanger and heater and cooler. Now I can do the summation of steam and cooling water that we purchase here. And now I change that put them together in terms of annual cost based on 0.1% return of investment. And the way to calculate that, based on this equation, annual cost will equal to the return of investment multiplied with the capital cost plus the operating cost. So in case of 6 plus 2, the annual cost will be equal to about $17,000 to operate a system of this. Okay. Now just leave it this way. This is the conclusion for 6 plus 2. Now what I do next is doing the loop breaking. Okay, refer to the combination of above pinch and below pinch. You can see some loop occur in this way. So in this case, if I combine these two heat exchangers together and get one, it means you have the heat transfer between these two regions. So if we have the heat transfer between these two regions, the heat utility and cooling utility will be changed because that is the interference based pinch consideration. So what we do, okay, now let's draw nicer here. So we would like to move that heat exchanger, transfer all the load here to that one. So if I transfer the load here to that one, this means this heat exchanger will be able to transfer the heat between these two streams up to 60 plus 80. So it becomes 140 kilowatt. If that the case, what will be what the system should change? So let's see. There are some change based on this line. Okay, and it's a change based on this line. So what does it mean? It means if the load, heating load change from 60 kilowatt to 140, the temperature outlet here should not be 150 as it used to be, right? When the temperature is not 150, so the heat load on this side should be changed as well. And that should be changed as well. How about this one? If the heat load changed from 60, the temperature outlet would not be 140 anymore. That will cause the change of temperature here, and the heat load, the heat in this cooling utility will be changed also. So let's see next. Okay. Now I combine. I move this heat exchanger to that one. So compare to this. Of course, if I move this to that one, this heat exchanger to this one, this unit, the temperature should be the same of 110. So this is to keep the heat load still at 140. Now the temperature become 110. If this become 110, so the temperature here should be changed, not 140 anymore. So what happened? I can write down Q equal mCp delta T. So the temperature right here will be equal to 113 degrees Celsius. Okay, 113 degrees Celsius. What happened? What happened? If I didn't do anything, we consider the temperature in and out between this transfer loop here, transfer unit here. The temperature is 113, temperature is 110. So what happened is the delta T between hot to cold stream become negatives, which give the different temperature violation. So we should do something on this diagram. So how to do? So according to what I mentioned before, because there is some heat transfer there is a heat transfer across the pinch line. So hot utility should be higher than 60 kilowatt. Now, if I put that 60 plus something, of course, based on this line, there would be some deduction on this heat exchanger. This just to maintain the heat load of this line, of this stream. Okay? Now, if I do that, what happens if I keep this heat load still constant? That would affect the utility, the cooling utility in the same amount. If you don't understand why they increase at the same amount, let's think about the composite curve. When you move the steam line to the left or to the right, when you increase by delta x by x on the hot stream, there will increase in the x amount on the below side as well. So now, how to do that? How to find out for x? Because the temperature here is already set at 113. So if I don't want the delta T violation, the temperature here should be higher than 10 based on the delta T minimum. So if I plus 10 here, it becomes 123. Refer to the transfer of the cooling down of this stream from 180 to 123. So I can get the x number there by Q equal to Cp multiplied with different temperature. So the x will be about 26.67 kilowatt. And now I can substitute to that and find out the temperature of this. And substitute x. Of course, when the x change here reduce, the effect, the x should be plus here, and then should be minus here to maintain the heating load for this streamline. Then when you change the heat load for each unit, they will affect. There's some effect on the temperature between these two units. So next, you have to calculate that. You have to find out for temperature on this and that. Alright. Now, using after plus or minus 26.67. So this becomes the final heat load. Look at that. The temperature, the heating load increased from 60 to 86 and 160 to 186. Alright, that's finished for the loop breaking number 1. Now let's see the loop breaking number 2. You can see that there is another loop here. What we can do here, before that, now we can reduce the heat exchanger from 6 to 5, 1, 2, 3, 4, 5, and 2 utilities. Okay, we do the loop breaking number 2 by moving this to that one. When I'm moving this to that one, what happened? Of course, the temperature will be something that you don't know. You don't know. When I move this unit to this one, of course, the heat load will be the summation of 40 kilowatt with the 120 kilowatt here. So it becomes 160 kilowatt here. However, the temperature would be not show up 140 anymore, and then the temperature here should be changed according to the heat load that's applied to this heat exchanger, because we don't have this anymore, right? So what I get is to calculate the temperature on this part based on the heat load of 93.3 equal to 4 multiplied with the temperature across this heat exchanger. So what I get is 126.67 right here. Alright. Then what we did, checking for the violation of delta T. Look like they're okay. 150, 130, and what else? Here is 126, and here is 94. So look fine here. So let's see. Now we have 4 heat exchanger and 2 utilities. And when you look at this carefully, you will see another loop taking place. Okay. Another loop taking place here. So how can I do? You can do many ways. One thing that I did is just transfer the heat to this one, and this to that one. Look at this. I will transfer the heat to this one, and I have to transfer the heat to that one. So when I transfer the heat to that one, it means the heat load will be the summation of these two. So it becomes 153 kilowatt. When that's changed, and that plus with this put together, so it becomes 260 kilowatt. So what happened now? When the transfer of heat to that, the heat load changed. So that one should be changed as well, because the number is is increased. This one should be decreased, but we don't know what it is. So just leave it in the question mark. So when this one changed, the temperature outlet would not be 123 anymore, and the temperature outlet here as well. Okay. So let's see what we can do. We have to find out that temperature first. How to do? we use based on this data, that is the summation of the heat load put together and the fixed temperature of 60 degrees Celsius. So we can find out for the temperature outlet. This is inlet, this is cold stream, so inlet, then we get outlet there. After we get outlet there, we can now find out, okay, let's complete this one first. So we can use that to calculate the outlet of hot stream. So we can calculate for this one based on the number that we know previously just now. So 151 minus 144 multiplied with Cp, and then what I get is Q equal to 20. And when I get this 20, of course, we will get the temperature outlet of this hot stream as well. Okay. Now let's check. Okay. From according to this diagram, so what I have is 3 heat exchangers and 2 utilities, which meet to what we calculate before based on the minimum heat transfer number of heat transfer unit equal to 5. So this is very nice. However, we need to check for the violation, and we found that some unit causing the violation of delta T. Where is it? The first unit look fine, huh? 170 minus 144 greater than 10. The second unit is 150. This is too high. Reduce the load here, because we want the temperature here to 140 at most. Otherwise, delta T will be violation. So that become less a little bit. We deduct some heat load out. When we deduct some heat load out, you have to take care of the flow. When you deduct the heat load out, of course, the temperature change. The cooling system change. But the deduction, of course, this should be plus, and then that would be plus as well. So we do the calculation for the x, and what we get is 13.3. We use 253 from the previous one minus x equal to 3 multiplied with the temperature across of that. So the x will be equal to 13.3, and then we substitute x in this equation, in this diagram, and calculate for the temperature less of them. So this is all the result. And of course, we have no more delta T violation. And now what we do? We have to calculate the cost of this network. We did the same. Okay. Now, in this spreadsheet, I already gave you the system of 6 plus 2 and 3 plus 2. So what I get refer to the calculation of 3 plus 2. I can get the annual cost around 22,000. So let's compare between 3 plus 2 and 6 plus 2 here. Of course, 6 plus 2. So many heat exchanger. So the capital cost of heat exchanger a little bit higher, not a little bit higher, very higher to compared to the 3 plus 2 system. How about the operating cost? Operating cost is mean more more utility that should be supplied to the system. 3 plus 2 will be higher a lot. So when we combine based on annual cost, we found that 3 plus 2 higher than 6 plus 2, around around $5,000. So this is the way they compare the work. So I didn't calculate in case of 4 plus 2 or 5 plus 2. So actually you can find out for the optimum heat exchanger and heater and cooler that should be in the system. Alright. I think based on this, you now understand how to do the calculation of the area and also the cost that concerned for each network. Thank you and goodbye.